Okay, good evening everyone, and sorry for the slight delay. Let's see if this works and we can get going. Yes, if you're wondering, yes, I am starting right on time, and that's exactly why I guess the timer shows 00 and not a negative time, because negative time would mean I'm late, and I'm not late, I'm on time. Yeah, that's the excuse I'm going to go with today. Anyway, so today's moderator is actually not KrzaQ. So I need to fix it. It's actually Foxtrot Charlie. There was some last minute change which for some reason slipped my mind. My apologies for that. Click. Okay, this is going to totally break everything. Okay, it should be fine now. Yeah. So yeah, my moderator today is Foxtrot Charlie. So if you do have any questions for me, then do ping Foxtrot Charlie, because he will be able to pass them to me using carrier pigeons. But to get the carrier pigeons, I do need to open my secret website with okay, now I will be able to even get the questions. That's amazing. Today's topic is going to be Better Zip. Better Zip is actually my CTF task from Google CTF 2019 qualification round, and it's the last of the 3 challenges which I've made and which I wanted to basically share with you on how to solve them and how they were created. There might be some more of Google CTF related live streams. That depends, I guess, on whether you would be interested in that. If yes, please put it down in the comments under the video once it's archived. And I might be able to, you know, convince one of the other authors to basically come and to join me on a live stream and to do their own challenges. Okay, let me think if I have some announcements today. I do have some minor ones. Well, first of all, there's no mission today again. Same like last week, I'm basically going with please go and solve a challenge I'm presenting by yourself on the Google CTF site. So yeah, and I guess adding a mission on top of that might be counterproductive unless you already solved that task. Then I apologize, there is no mission. Yeah. Apart from that, there will be no live stream next week, and but there will be one in 2 weeks, and then there will be again a break for about 2 weeks with no live streams, and then the live streams will be back again for I think almost a whole month. We'll see. So that's basically how it goes. Now, I know I have one more link to share with you, but okay, let's do it like this. So, first of all, this is the website of Foxtrot Charlie, my moderator. The URL is super easy, you can easily type it. So, okay, I'm going to actually give it to you on the channel as well, on both IRC and YouTube channels, yeah. And wow, there is actually a new post, or is it just modified? Mission 16, that looks like it was just modified, but it wasn't really written at that time. Foxtrot, are you trying to pull a fast one on me? It seems so. I know that he did write something, yeah, on the Polish side of the blog, but I guess I'm not really convinced this is a new one. Yeah, but this is his website to bookmark it and look there from time to time. Okay, so if you don't know, I have this Google groups called Ciekawe papierki. In Polish, it's actually like interesting papers, like interesting scientific papers, and I basically send links to it, and Foxtrot also sends links to it with interesting security stuff. Some of it, like this one, is in Polish, but most of it is actually in English. If you're interested, you can join. And the newest one is pretty interesting. It's a new paper released, I think, yesterday evening-ish. Speculative buffer overflows, attacks, and defenses. I do have it printed. I do not have it yet. I didn't read it yet. but from what people tell me is that the authors of this paper actually got a nice hefty award from Intel for their research, so do check it out. And just in case you'd actually like to subscribe to that group where I'm sending links, the idea behind that group is basically that I'm sending the links, so I'm going to, that I want to add to my to-read list. They are usually like electronics related, security related, hacking related, or programming related. But I keep it public. You might want to join anyway. I know that there was like a few hundred people already following this group, so yeah. If you have some really super interesting links, do send it to the group as well. And I guess that's it, actually. So before we get to the main topic, I am going to give it at least 3 more minutes so that folks which do want to be here from the beginning but are running late to arrive. So let's go with the questions, I guess. So you will see the questions down here. And the first question is, have you heard that in 2015 there was a rootkit found in the UFI of many Lenovo computers? I actually didn't. I did, well, I guess 2015 it was one of the years where people were starting to look at what do well, vendors like Lenovo or HP or other Toshiba or other providers of laptop, what do they actually include in the bundle when you buy a laptop with Windows and so on. And but yeah, I don't remember this specific one, so it's quite interesting that they squeezed it so low in the stack. That being said, it's not super surprising. So yeah, if you have any more information, like a link, Przemek, then do let me know. I've heard that compression may be used to make reverse engineering harder. For example, some versions of Intel ME did use Huffman with dictionary stored in the hardware. Is this possible? Yeah, from what I've heard, that's true. Actually, that's why the firmware wasn't decrypted for a long time, like quote unquote, and decrypted, because the tables for Huffman were in the hardware. That being said, yeah, basically it does make reverse engineering harder. Basically, in reverse engineering, if we think about software reverse engineering and binaries, there is little difference between encryption and compression. It's just obfuscation, like both of them. It doesn't matter if it's encryption actually or compression, because in case of encryption, you actually need to store the key there anyway. So that doesn't matter. It's not really encryption. It's like encryption with a stored key. And compression is just, like pretty much the same thing, just a layer of obfuscation. So from that perspective, yeah, you can do that. If you additionally can actually store the compression table in the hardware, that's even better. The question is, I'm not really sure if in case of Intel ME that was supposed to be an obfuscation. Perhaps it was just done so the firmware can actually fit into the ROM of the chip, because usually ROM is you don't have too much of it, so you do want to apply compression to make sure that everything fits there. And that's true for BIOS as well. Like BIOS also has compression, but it's actually done in the software if I remember correctly. So I'm not too surprised to hear that compression was there used. I'm not convinced that it was for obfuscation. I'm pretty sure that it did. If it wasn't implemented in hardware, I'm pretty sure that it was actually made reverse engineering harder. Can you share some resources for Active Directory pen testing? Actually, no. This is an area which I basically never looked at. Like, yeah, for some reason, Active Directory was never in my scope. So I have absolutely nothing for that. You might want to. Yeah, I'm wondering if I know some folks who might have done something in there, but I'm not really, I guess. Did you get more answers from Dragon Sector about solving time for the tasks on the CTF? Not really. I didn't. I didn't get any. So only what I said last time. I'm curious how much time approximately you've spent on solving beginner's quests originally compared to the 3.5 hours on the stream. I think it was a little less than twice that time, basically. So I got stuck on the OCR one. The one I've solved on the stream was actually easier, and because the quality was much better, and the one which I did before, the quality was a little worse. So the OCR did have some problem, and the flag was actually in a different place. So that one I did get stuck on the some of the exploitations once I did actually spend more time on them before I found the bug or found the exploitation technique which I should have used. Especially the ones near the end, like the last one where you had to, when I showed it on the stream, I actually did, you know, a pipe, and then I blocked writing to the pipe, and that way I blocked one process in a semi-controlled place, and it actually took me an hour or a little more to figure out that trick, like that I need to use that trick, because I wanted to do just a normal race condition, and it didn't work on the execution environment of the task due to process restriction limit or CPU limit or something like that. So yeah, I tried like different ways, and in the end I decided to just go for this trick. So yeah, I guess around 6 hours-ish. I'm always asking myself why the documents are called paper when they are released 99.9% in digital form. Why aren't they called documents? So technically a document also was, you know, in a paper form, right? A document isn't something related to being digital, but I guess in both cases is actually just historical things, right? Yeah, like I don't think there is another answer to that. Like historically you did print them on paper, so you called them papers, and it didn't matter, the medium didn't matter, like the type actually, or the things you had on that medium did matter, so that's why they kinda ported the same name, like documents or papers, to current digital media, right? Kind of the same as we have still the save icon being of a floppy disk, which I guess to newer folks doesn't make a lot of sense. Ginvale's alphabet, letter Z. Okay, do I know anything security related for letter Z? Z. Seriously, you couldn't go with D? Let me think on this one. Z. What's security related on Z? I seriously need to prepare a list of things. I don't know. I will think about it. Z3, Dohan says Z3. Okay, let's go with Z3, why not? So Z3 being... I will actually be using Z3 today, so that's a good thing. 0 day is another idea. Okay, so I will be using Z3 today anyway, so let's not go there. Let's go with 0 day, which I also like. 0 day, as you know, is basically a type of a... It's basically a vulnerability which was discovered and not disclosed until a certain point in time, and the moment of disclosure of a previously unknown vulnerability is called the 0 day. And so 0 day vulnerabilities mean basically vulnerabilities which were not known before by the wider audience, by the vendor. They are unpatched. There are no patches or defenses against them, apart from general defenses, obviously. So yeah, that's a 0 day, and there was some discussion in the past if a vulnerability is being disclosed and it's called a 0 day at that day, right? Because 0 days from disclosure, should we call it a 1 day the next day and 2 day in the second day and so on? But I guess the idea is that it's being called a 0 day until it gets patched, and then it's just a normal vulnerability. Cool. I guess we got to the 15 past, a quarter past, so that means we should get going with today's subject, but we will get... I will get back to the questions either somewhere in... probably not in the middle, probably at the end of a live stream. Cool. Let's start with downloading the challenge. The challenge was called Better Zip. It's the legacy zip crypto is long broken. So we fixed it. Perfect. And there's an attachment, and it was solved by 38 teams out of, I think, 270 teams had any points with give or take. So more than 10%, like around 15% of teams actually solved these tasks. So okay, let's download it. Now there is one thing which is quite curious, which you did notice in the comments, and we did notice at the at the CTF as well, is that when you download a file from the site, you actually get a zip extension, but only in Chrome. The file from the server doesn't have any extensions, and for some reason Chrome actually decides, oh, it's a zip file, I'm going to add an extension. So that's pretty interesting, because Firefox doesn't do it. And there was a comment, for example, about the files being corrupted, because on the live stream I did show that they have a zip extension, but if somebody downloaded the file using Firefox, they do not have a zip extension. What's up with that? And yeah, that's actually Chrome adding the extension. That's really weird, but yeah, there is some mechanism like that in Chrome. Cool. So just to give you some more idea, I basically was thinking of, when making this task, I was thinking of like, hey, let me make a task which has stream cryptography, so not block-based cryptography, but stream-based cryptography, because the old zip actually had this kind of cryptography. And like a couple of weeks, months, I guess in May, on my channel, I did a presentation about zip, and I did explain how the zip crypto works. And while preparing for that presentation, I actually did read the original paper on breaking the zip encryption and the follow-up paper, and I was actually I really liked it. So I decided to make a task which also has this kind of stream cipher to it, but it's different. Yeah. So in the end, I couldn't figure out how to approach it. I did have some ideas, but I ran into some problems, and I decided to like just look at this book and by Jean-Philippe, right? And in the somewhere around this point, there is a chapter on stream ciphers, and I read a couple of pages, and I'm like, let's do this. And the thing which I done is called linear feedback shift registers or something like that. And yeah, this is basically what we will be looking at today. I probably bragged already about it, but hey, look, I actually do have an autograph from Jean-Philippe on my book. If you're Polish, then the book actually came out in Poland on under the Polish title of Nowoczesna Kryptografia, which means modern cryptography. I don't know, like a week ago, last week, I think. And yeah, there's even my logo on the book somewhere here. Yeah. Since I'm one of the, I guess, partners, it's called, or patrons actually, of the book. Cool. Okay, so it's downloaded. Now we can start looking at it. Let me just extract it if I find the proper directory that is. Okay, here we go. So I guess I can show you the file manager. Just let me close some tabs like 0 days in SSH, 0 days in Apache, and so on. So you don't know that I have any 0 days there. Here we go. Okay, so yeah, this is basically what we get. And what we get is betterzip.py, which is an implementation of the zip file format. It's a compressor for the zip file format with the fixed cryptography in there for encrypting a zip file. And the flag.zip is actually the file which has been encrypted using that better cryptography, right? So if we look at this, we see that there is the PNG file, because by default, even if you encrypt a file with zip, it actually doesn't encrypt the name. So the names of all the files in the archive are actually plain text, which isn't great, right? So we know it's a PNG file and it's of this size, and this is actually really important in this task to notice that it is a PNG file. Then if you try to extract it, obviously you need to enter a password, and that doesn't matter because even if you enter a password correct, well, the total commander, which I'm using here, doesn't have the implementation of the same algorithm, so that just wouldn't work. And yeah, here we have the better zip implementation. So I guess this can go here. Oh, we can do one more thing. We can do zip info on zip info -v on the flag file. And zip info is the info zip, is from the info zip package, and it basically shows you some details about the archive. It's not great as in the amount of details you get, but it's actually pretty decent. So yeah, what we see here is that it requires version 9.0 of a zip archive to actually decode it, and there is no such thing. Yeah, I just put 9 over to signal that, hey, this is actually not the original, like any original zip version. I think like 7 something is the newest one, or 6 something. Yeah, and what else we see? We see that it's stored. There is no compression here, and this is quite important because we will be doing a known plaintext attack, or actually a partial known plaintext attack. So knowing that it's not compressed, this makes it really, well, not super easy, but easier than if it would be compressed. If it would be compressed, then the task would be harder. I'm not sure if solvable, but harder. That doesn't mean that the algorithm is good here. It's just that a single file might be not enough to break it. Okay, then yeah, we have some more information. The uncompressed size is actually 93 kilobytes with 674 bytes, but the compressed size, and again, it's not compressed, so this is the stored size inside the zip file, is actually almost, well, not really, like 70 kilobytes more, 70 bytes more. That means there's at least some header or footer which has been added to the data. That's pretty normal in case of zip, in case of encryption, regardless of whether it's actually like the normal encryption, the legacy encryption, or something else. And I don't think there's anything interesting here apart from that. So yeah, knowing that, we can, I guess, go to yeah, to looking at the code. So I guess we can start looking from the bottom, the very bottom. There is 200 lines of code here. I am going to go through part of it. I am going to tell you what the other part does. This is, by the way, a compressor. So it takes the file which is supposed to compress, and it compresses it. Yeah, that's basically all it does. And it grabs a key as well. So it takes the archive name, the file you want to compress, and the key as a hex string. So the key has to be in hex. And then it calls better zip creator, add a file, and closes the archive, and that's basically it. So if we look at the creator, this is basically the class better zip creator. This is basically a generic zip archive compressor. Well, not really compressor, creator, right? So I'm not going to go through it because it's as generic as it gets. There is nothing weird here. It's just a normal zip file. You can read through it. The code isn't magnificent by any means. Yeah, here is like the version 90 is actually 9.0, and yeah, the encryption is so good, it's version 9.0 at least, and super strong encryption enabled. This is the flags bit. No compression, yeah, and some other stuff which we don't care about. What we can look here at is that there is this string, which is again LFSR. It stands for linear feedback shift register, and it's a way of I guess generating random bits, which can be also used for a stream cipher. So a lot of stream ciphers work like this, and this is quite important actually for this task. So you basically have the data which you want to encrypt. And let's assume that the data, for the sake of the discussion, let's assume that the data is split into bits, not bytes, but bits. It doesn't matter too much, but let's assume that. And therefore, what you need to do is you need to create some kind of a pseudo-random pseudo-random number generator, or bit generator in this case, and initiated with some key. So the seed for it, for the PRNG, would actually be the key. And then you generate basically the same amount of bits as is the length of the data in bits. And then what you do is you basically XOR one with the other. So you you do an XOR, like XOR this bit, XOR the next bit, XOR basically all the bits. This is XORed as an XOR, or however you want to call it. And the output of XOR operation is going to be obviously the same size, and is going to be your encrypted data. The question in stream ciphers, this is by the way not only used, this scheme, it's not only used in stream ciphers, it's also sometimes used in block ciphers, but it's pretty popular, not the only one, but pretty popular anyway. The original zip actually also did the PRNG of it, actually also used the data, which was here, to reseed itself. This is not the case for my task. I actually do not look at the data. The important part is only that I generate this XOR stream. So if we generate the identical XOR stream, we basically can decrypt the data. That being said, if we know some of the data, and again, it's a PNG file, right? So we will know at least the header, we will know the end, we might guess some strings in the middle of a PNG file because of how the PNG file is constructed, and I will get to that later. And given that we know the plaintext data, as in the yellow stuff here, right, then we will be able to XOR the plaintext data with whatever was, with whatever is in the file, the encrypted stuff. And if we XOR them, what we get is we get the key, like the part of the key stream. Now, if we get that, then that means we can maybe reason about the state of the random number generator, which was being used here. And this is basically the idea of the attack. Now, what we are missing is the details. So let's go now into the details. And the detail number one is actually what is LFSR and how does it work. So it's like this. You get a register, like think an assembly register, and the register can be any number of bits. Let's assume for the sake of simplicity that it's actually 4 bits, because why not? So this is bit number 1, bit number 2, bit number 3, and bit number 4. It's at the beginning initialized by something called the IV, well, the initialization vector. I'm sorry for my pronunciation. So let's assume that at the beginning we have a 1 here, we have a 0 here. It's bits, right? So 4 bits, 1 here, and again a 0 here. Now, when you so this is the register. It's again, the name is linear feedback shift register. So this is the register part. Now, if you want to actually get a number out of it, what you do is you grab the most significant bit. In this case, it would be a 1. So 1 is our random number. Let's note it. And then what you do is you shift the registers by 1. So you do like a shift by 1, which means that the 0 goes here, the 1 goes here, the 0 goes here, like this 0, right? I'm just shifting. So this goes here, this goes here, this goes here, and we like add an additional 0 at the end. Now, in the place of that 0, this is the shift part. In the place of that 0, we actually need a new number. Otherwise, we would just, after calling it a couple of times, we would get always zeros, and that's not really a random number. So what we do is we select a couple of these of the bits in the register. Let's assume I'm going to select this one, and this one. So these three. And what you do is you basically XOR them together. And you additionally XOR it with 1. So you calculate something like this. 1 XORed with bit number 3, XORed with bit number 2, and XORed with bit number 0. And you always take the same bits. You choose it, which bits are you going to take. And the selection, the set of the bits which you chosen is called a polynomial. So the polynomial, because you can write the same in the form of a math equation, basically, which would be 1 XORed with, or actually like more like p equals 1 plus b. Well, let's do it like this: c0 times b0 plus c1 times b1 and so on. So in this notation, the c0 might be 1 or 0, 1 meaning I selected this bit, and 0 meaning I didn't select this bit. So in our case, we selected 0, so this would be 1. And I didn't select bit number 1, I never selected this one, right? So this would be 0. And plus is actually XOR. It's plus because we are operating on bits, so it doesn't matter. Plus and XOR work the same way on one bit, and multiplication works the same way as an bitwise AND instruction, like AND, right? So yeah, but you might note it with multiplication. And b0, b1, and so on being the actual values from here, right? So the c0, c1, these are constants in the polynomial, and b0 and b1 are the actual bits. So in our case, and please look at this row, it's actually b0 is 0, so here we would put 0, or here, right? Then we have b2 being 0, so this is 0, and b3 being 1, so this is 1. So yeah, what we XOR is 1 XORed with 1, and 1 XORed with 1 gives us 0, and 0 XORed with 0 gives us 0, and whatever we get as the result, and the result here would be 0 actually, we put it here. As instead of 0, we actually put the result of calculating that polynomial, or like the simple bitwise operation, right? So in this case it would be 0, but if we would like shift it again, then we get 0, 1, 0, and 1, and from that we would get yeah, probably 0 again. So the funny thing here, and why this is partly normally not secure, is that for certain register lengths, you do need to select specific polynomials, because if you don't select a specific polynomials, you might get really, really bad random number generator. But actually, this is not what the task is about. It actually helps a little in this task, but you don't use this, what I just mentioned. Because, as we will soon find out, we do know the initial state of registers. We don't know the polynomial, and the polynomial is what we will be trying to find, or actually the C values, and this will be the key which was used to encrypt the data. Anyway, so yeah, basically this is how LSFR works. You do shifts and you calculate the new bit. You shift, you calculate the new bit, and each time the output from the most significant bit is your random value. Cool. There's a question: is normal standard zip encryption that very insecure really? It is prone to the known plaintext attack. If you know, I think around 13 bytes usually of the compressed data, that means yeah, you break it in a couple of minutes. Do look at my presentation about the zip files on my channel. And if there is a section about that one where I actually show how to break it. And it doesn't matter, the password length doesn't matter because you break the key and not the password. If you don't know what's the distinction between a key and a password, the key is usually of a constant length and password isn't, right? Because the password can be ASDF, but it can be something really long. So there is a password-based key derivation function, which is usually used on the password to get a specific size of the key, which is then used for the encryption. And this is also what was going on in zip. And you break the key using the known plaintext attack. Okay, so let's look at how exactly does this LSFR cipher work in this case, right? Because what I told you was the theory behind it, and a rather shortened theory at that. But what we really need to know is how it exactly works. And there's a class called LSFR cipher, and it takes the key, and it takes the poly size. Now poly SZ is here, and this is actually the size of a register in bits. So the register is 20 bits. If we then look at what's going on, let's look from the top up. So yeah, we initialize it with the key and the size of the polynomials. Then we get some headers, whatever this is. Then we encrypt the data, and this is the encrypted data. Then we calculate the hash of the data, of the unencrypted data. So we calculate the hash of the unencrypted data, a really strong hash. This is a good hash. And we encrypt the hash as well, using the same object. And then when we store the stuff, we actually write the crypto headers, the encrypted data, and the encrypted hash. So both the encrypted hash and the encrypted and the crypto headers are the things which were added to the beginning and the end of the data stream, which I guess explains why these two numbers here differ, why the compressed size and uncompressed size is actually different, right? Because in the compressed size, we added the crypto headers, whatever that is, and the encrypted hash of the data. Cool. So now let's look at the implementation of this thing. It says here, I guess the initial poly size was 8, but we know it's actually 20 for us. You can give it the key IV and the cipher IV. So we know there are at least two initialization vectors here. It checks if the length of the key is less than poly size, and if it is, then it says that yeah, the length of the key must be at least 20. Well, the poly size is actually 20 bits, but the key size has to be, in this case, 20 bytes. So the key is super long, right? 20 bytes, that's a lot. So we are not going to brute force the key, because it's like 20 bytes, you don't want to go brute forcing 20 bytes. Okay, then you put the key in a bit stream. What's a bit stream? It's pretty obvious, but I will, I guess, discuss it in a second. Then if the key IV is not set, and it is not set in our case, then it calls urandom. Urandom is actually a cryptographically safe pseudo-random number generator, so there is no way to break it. And this is the usual assumption you make. So yeah, they call it for the poly size, and they get the key IV, and then yeah, make a bit stream out of it as well. And they do the same for cipher IV. If the cipher IV was not given, again, we grab 20 bytes from the system's pseudo-random number generator, be it like def urandom on Linux, or be it whatever crypto API is called on Windows. And after that, we actually create not 1, but 8 of the LSFR random number generators, 8 of them. Right? So yeah, 1, 2, 3, 8, this many. Yeah, not 1. And this is quite important. And we initialize it, I guess, with yeah, I'm going to check what exactly are the arguments, but there will be at least 3 arguments. The register size, and I guess this is it, this is the register size, is going to be 20 bits. And then the polynomial, which is going to be used. So which bits do we select for making the feedback, the linear feedback, to get the new bit at the end? so polynomial, and then the initialization state, the initial state of that of the register. Because, you know, after some time there will be only new bits, but initially you need to initialize it with something ideal which is not zeros, because if you look into it, it cannot be all zeros, because zeros always give zeros regardless of everything else. Which isn't fully true, but let's assume it is. Okay, so we create 8 random number generators. This probably is the polynomial, and this probably is the IV. And then when we get a byte, when we want to get, like, generate a byte to encrypt the data, we actually call all of the 8 random number generators one after the other, and we get a bit out of them and shift the bit by I. So that means that the 0th pseudo random number generator, the 0th LSFR, is responsible always for generating the 0th bit. So each bit of the byte is going to be generated by a different random number generator, which is fine. And then when we actually encrypt the data, what we do, this is the crypt function, we generate a byte and XOR the data with it, and that's basically it, right? Because the data is a byte array, and for the length of the data, generate the byte, XOR it, and return the data. So this is the scheme which I did describe at the beginning. So we are, I guess, we kinda know already what is going on. What we need to check is, again, the implementation of LSFR, and it is like this. There is the get bit function, which is basically the only function here. Yeah, we initialize it with giving it the polynomial, so this is the polynomial. Giving it the initialization vector, which is R. R is the register, so this is the initial state of the register. And then it also, like, calculates the mask because of the size of a polynomial, right? The mask is just like all the bits, 20 bits set, for example. So if the size would be 2, for example, then we would have 1 shifted by 2. 1 shifted by 2 is obviously this in binary. Yeah, 1 with 2 zeros at the end. And we subtract 1. This is actually a nice trick to get all the bits set of a given number of bits. So this subtracted gives us 1, 1, which means, like, we have 2 bits set. And this trick works really nice for any size. You can check it out. Okay, then looking at the get bit, what we get is the bit itself is the register shifted by this number of bits. It basically grabs the most significant bit of the register. So this is the size of the register minus 1. That means it selects the 19th bit in our case. And yeah, it grabs, like, the only 1 bit, right? Makes sure that this is just 1 bit. It will be only 1 bit, but it makes sure anyway. So we get the bit which is then returned. And everything else, like this part, is actually the linear feedback part, and the shift as well. So the new bit is first initially equal to 1. You did remember the polynomial which I've written is 1 plus whatever is the polynomial, blah blah blah. This one here, right, is actually this one. Then masked, we get the polynomial, and we mask the, basically do an bitwise AND on the polynomial and the register. So we select the individual bits, and we make sure that the bits which are not selected by the polynomial are actually zeroed, because this is how bitwise AND work, as you know. And then for all the bits, what we do is we XOR the new bit with the selected bit. This is just selecting the ith bit from the masked register. So it XORs everything. If it's by the way, well, it could be one of the 3 things, right? It's a selected 1, a selected 0, or it's 0, which is there due to the AND actually being applied. And if it's just an AND, then XORing whatever with 0 doesn't change it. So if we XOR 0 with 0, it's still 0. If we XOR 1 with 0, we get 1. So XORing something with 0 doesn't change it. That's the way XOR works. So this is why this is legal. And in the end, we create a new value of the register, which is the register shifted by 1. Yeah, shifted. Well, actually, I should show it like this, shifted. And at the bottom bit, we insert the new bit, which was calculated here. And yeah, we then apply the mask to make sure that we still have only 20 bits, because otherwise, after this shift, we would have 21 bits, and we added this new, but we are only interested in 20 bits. This doesn't really matter. I mean, worst possible scenario is that this number grows really, really huge, and we don't want it to grow, but apart from that, it would work okay. Okay, there's a question. Blame Drop writes, I've tried solving it, and I have a question. Why first 20 bytes could be decrypted without with any key? This is a really good question, and especially for the place where we are now. I will get to it in a second, but if you remember what I was like talking about before, if we had the 4 bytes, right? Sorry, the 4 bits in the register, in the linear feed shift back register, and it had some initial value. Please note that the first 4 times we call it, we actually get 1, so this value, then we get a 0, then we get a 1 and a 0. So the first register length of times we are going to call it, first 4 times in this case, for first 20 times in our case of a task, right? We are going to get whatever was in the register. And it doesn't matter what polynomial you use, because the polynomial is just backfilling the register, but we already have 4 values which are ready to be extracted, and they are never touched, because only the last byte is touched, and this is happening after the shift. This means that, well, whatever is the initialization vector is going to be what is going to be outputted, calling it by the first 20 times in our case, right? So yeah, it doesn't matter what polynomial it is, you will always be outputted the 20 bytes of the initialization vector at the beginning, and this is not related to the polynomial. This also unfortunately means that the first 20 bytes of the file of the known plaintext of the PNG are useless for us, because they will not give us any information. We already know what is there. Why? Let's look at the headers. So let's go here and get headers. This is, as you remember, written in the file before the actual data, right? Before the encrypted data. And the headers give us the key IV and the cipher IV. And the cipher IV is what is actually being put in the register. So, yeah, we already know the first 20 outputs of a linear feedback shift register, and they are totally not related to the key. Note this is the key IV and not the key. The key is not written in the file. And this also means that because we already know the 21st outputs of the linear feedback shift register, we don't really care about the first 20 bytes of a known plaintext, because we do not have to reason anything, we do not have to derive anything, we already know the state of a pseudo random name generator. So that means that that header I mentioned, that we actually know it in the PNG, the first 20 bytes of it, well, they don't matter, because we can just decrypt them. And this is quite unfortunate, because that also means that, well, we will not be really able to use our knowledge of the first 20 bytes of a PNG header. We will have to rely on whatever is after the 21st bytes. But before we get there, because for some reason I'm telling you all the time that, hey, if you know the bytes, you can maybe reason about it. And this is actually true, because the LFSR, the linear feedback shift register, is not a secure it's not a secure cipher, it's not a secure pseudo-random number generator by any means. As in, if you do know the polynomial, and you do know, it's like this, if you know the polynomial and you know the output of it, then that's it, like game over. If you know, especially like the register size of the output, so 20 bytes in our case, then that's game over. But we do not know the polynomial. So for us, it's going to be a little bit harder because we need to get more bits than just the first 20. We do know the initialization vector, we do know the first 20 bits, that means we need to get some more 20 bits, and what we can do is we can create an equation, like a math equation, which goes like this. For what polynomial would this output be generated? Assuming that this is the initialization vector, and this is the equation which we are going to solve. Are we? No, we are not going to solve. Z3 is going to solve it for us. For us, we are just going to create that equation. But to create that equation, we do need the output, and to get the output, we do need the plaintext. Because as you remember, the plaintext has been XORed with the output. That means what we have is the plaintext XORed with the output, and we need the output. So to get from that the output, we need to XOR it again by the with the plaintext, the known plaintext, and then we get the output, and then we can put that output in the equation and try to find a polynomial which would actually be, well, actually 8 polynomials, right? Because we have 8 random number generators, which would give us the this result, the output of the result. And it's actually a little funny because we don't need exactly 20 bits of 20 bytes of output apart from the beginning of a file. I'm going to ignore the beginning of a file. I'm going to say like 20 from time to time. But if we know the next 20 bytes or whatever 20 bytes in the file, then we have a pretty decent probability of getting the right polynomials. If we have 1 byte less, then the probability falls. It doesn't fall drastically, it basically halves, which means that if we, for example, are going to find only 18 or so known bytes, then it's still pretty much brute forceable. If we find 10, then it starts to be dicey. So the more bytes we know, the better. Yeah, so I might be sometimes mixing up bits and bytes, but in this case, if I'm talking about bytes, that means that I'm talking about all of the 8 random number generators which are used here. If I'm talking about bits, then I'm talking about the one single LFSR. We will be doing equations for each of the LFSR, and we need 20 bits for all of them, which means 20 bytes for, yeah, or like 20 bits for each of them and 20 bytes for all of them. Okay, now the last thing which I didn't show is the bitstream. It's basically just a class where you put in bytes and you can get the bytes bit by bit, and that's it. It doesn't do anything more than that. It also has a like nice convenience function called getBits, which actually calls getBit the amount of time you tell it to, and returns a number. So that's about it. So yeah, this is what we have to work with, and I'm actually going to copy the file and name it like go.py, and we will be operating on the go.py and not on the betterzip, because I don't want to modify it. So let's start with actually reading the zip file, because this is the writing of the zip file, and I do not want to, I do not want to handle that. So let's I do not care about writing, right? I care about reading only, because we need to read that zip file. So this goes away, and now we need to read the data. Now the way I'm going to do it is rather nasty, because I am going to copy the zip implementation from Python. Python has actually a zip file implementation. I cannot use it for this file because of this file, like directly. Well, I can show you why not. Import zip file. Zip file, I think that's called just zip file flag.zip. And so this is Z, and I think it was called extract, and I give it flag.png. And it should extract that file. I don't remember how exactly it works. Do we have a Python zip file? But we will still use it in a little different way. So this is, no, I'm using like 2.7 as usual. Open, extract, member, okay, to the current number, the current, no, I don't want it, I want to read it. Returns the bytes of the file name. Okay, this is exactly what I want. So I want to read the flag file, and let's try to run it. Do I have a console open? I do have a Linux. Well, that's fine. I'm probably going to use a Windows one later on. Yeah, and it says that the flag file is encrypted and the password is required. Now, what I know that, right? It's obvious. I know that. What I want is I want the data anyway. I want the encrypted data because this is what I will be working on. And to do that, I'm going to copy the implementation of it. So I have actually no idea where is it. So let's do strace e trace equals file output to some logs and Python go. Okay. And now I'm going to cat logs grep zip file.py, and it says it's here. Okay, perfect. So I'm going to copy that file from there to here and open that file, and let's change it a little. Now the nice thing is that Python will actually start to import this file from, it will use the copy which is in the current directory. And I want to first of all convince it that, hey, it's actually not an encrypted file, sorry. So what's the place it complained? Where's my, sorry, I'm going to move this console to more here. Well, I guess you don't see it now. Let's move it here in that case. So it complained at this line, 990. Yeah. So it checks if it is encrypted and not password is given then something. Let's actually do like if false. Let's never go here. It's not encrypted, just ignore it. And let's try it now. Go. Now it says it's a bad checksum. It is a bad checksum because I didn't decrypt the data. But again, please don't do it at home. But what's the number of the line? Oh, here we go. Okay. Yeah. And what I'm going to do is like I'm going to say, yeah, like it's a good checksum. Perfect. So now it works. Now I have the data, print length of data, which is exactly the size of zip info -v flag grep. Yeah, which is the size of uncompressed data, right? Sorry, no, the compressed data, which is fine, which is exactly what I wanted. Now I'm going to extract the headers, and the headers are what are the headers? It was the key IV and it was the cipher IV. So the key IV is the first 20 bytes of the data. The cipher IV is the next 20 bytes of data. And then we get the data, and at the end of the data, we have the SHA-256 checksum. It's encrypted, but we have it there. So, but I guess I'm going to leave it there for now, because it's actually going to be deciphered with, or am I going to leave it? Yeah, I guess I can leave it. I'm going to leave it there. Or am I? I don't know. No, I'm going to get it like mcache. So that's the 256. How many is that? 256 by 8. That's actually 32 bytes. So from the last 32 bytes to the end of it, that's my encrypted hash. And the rest of it is actually the data, right? So from 40 to -32, minus means like from the end is this. And we can check if whatever length we got here, is it equal to the uncompressed size. Okay, 674, 674. Yeah, that's fine. So we get the header. And now we need to do the magic. The question is, do I have Z3 here? Import Z3. I do have Z3 here, so I can use Linux. Oh, I see I have zip file already imported here. That doesn't matter, because I can remove it. So now what I need is what I can do is I can decrypt the first 20 bytes of the file. I can just decrypt it because I know the initial state of the register, because it's the cipher IV. This is it. This is just the first 20 bytes of a key stream, which is used for encryption. So I'm just going to use it to decrypt the first 20 bytes of a file. Now, if you're wondering what key IV is, it was somewhere here. It was actually here in the part I removed, I think. No, it is actually here. Yeah, it's here. An initialization of this. It's actually the key IV is being XORed with the key which the user provided. So the key IV is just something to obfuscate the key a little. A quick reminder, what is Z3? You will see. Z3 is SMT solver, basically. Long story short, you feed it a math equation and it gives you the results. That's not the full story, but we can use it as like that today. Yeah, and it's from Microsoft, and it's, I think, open source right now. Cool. Now, what was I about to do? I wanted to XOR the stuff, right? So, byte stream of the data. Let me just grab like the header of the data, like the beginning. Start is the easier word. So data 20 bytes up to 20. No, up to 20 bytes, and I want a byte stream. A byte array, sorry. Here we go. And then we have already the key for that, right? So the key for that is the cipher ID, and I want a byte stream of the cipher ID. Sorry, byte array. Okay, and I think I can just XOR it, so for I in range, or X range of 20, start of I, XOR it please with key of I. Yeah, and now I want to write it to some file, so with open dump.bin, or like header.bin, or start.bin, or png, whatever, doesn't matter, as f write start. Here we go, let's run it. Okay. And we have the file. I'm going to open it in the hex editor. And something didn't work. Because yeah, it didn't work because I need to do them. The bits are in a little different fashion. So instead of doing this, I can just do this, like what's going on here. I can initialize it and I can decrypt the data. So yeah, because basically if you look at it, the first 20 bits actually go to the first register, right? And what I've done is I did an interlacing, which doesn't make sense. So I'm going to use the code which is already here to do my bidding, basically. And again, as the question went from the beginning, is that from blame drop, is that it doesn't matter what key you choose for the first 20 bytes, because the first 20 bytes are reliant on cipher IV only. Okay, so what do I need to give it? I need to give it the key, and I don't know the key. I don't care. Like A times 20, that's fine. Then I need to give it the poly size. The poly size is already 20. Well, I do have the macro, so let's just use it. And then I need to give it the key IV, which I again do not care about. I can give it none. And then I need to give it the cipher IV. So here we go with the cipher IV. I do not need it in this case. And then I can crypt it. Well, in case of ciphers which are constructed like this, be it block ciphers or like stream ciphers, encryption and decryption is actually the same operation, which is just XOR, right? So I can use the crypt, means both encrypt or decrypt depending on the context how you are using it, but yeah, it's the same thing in these cases. And now I need to give it the beginning of the data, so just first 20 bytes, and it will give me some start. So let's call it like this, and let's see if it makes more sense now. Okay, yeah, so what we got is the PNG header. This is the PNG header. If we would decrypt more data, then it would actually start using, you know, the actual polynomial, the bits which are generated by the polynomial in the LSFR, and we would just get gibberish. So this is all we know. And I guess we can try to add structure. No, there's this. I don't know if this program actually understands PNGs. Let's see. Select structure library. PNG, no PNG? Oh, come on. Okay, so it seems there is no PNG, so I'm going to just have to walk you through it, or let's just go to PNG specification. Oh, there's the W3 about it. That's cool. Wikipedia actually also is pretty decent when it comes to this. So let's go to Wikipedia, and we have file header. Yeah, so the file header is, this is the magic value basically, and it's pretty cool how it's constructed because it has the PNG letters in it, and apart from that it has a byte which has the high bit set to detect if you're passing it through a medium which is not 8-bit medium, like 7-bit only medium, and it has a DOS new line, so if it's broken, like it's actually recoded from a binary file is recoded from a Windows lines to Linux lines. This should never happen, but sometimes it does. Then it will be detected by this change in the header, because this would actually be converted into just A without this. Or like if the other opposite direction happened, there would be another OD here at the beginning. And yeah, this is the header, and it's 1, 2, 3, 4, 5, 6, 7, 8 bytes. So we know that the first 8 bytes are useless anyway, because this is the header, and they don't give us any information about the file. Now, the rest of the PNG is basically created in the following way. It's a chunk-based format, which means that the PNG is split into blocks, right? Where the blocks are, the blocks basically have a header and have a footer. The header of the block is the length of a block. Here is the length of I'm seriously lying to you now because this is not correct. Yeah, now it's correct. This is the length of the block. It makes more sense now. And then there is a 4-byte tag of the block. A tag is basically like some identifier. In this case, it's header, which means it's just a header. Like PNG header. And then there is the data, and we do not have this part of the data, but thankfully it might be easy to guess it. And then there will be somewhere, like after this many bytes, I don't remember if this actually includes or doesn't include. I think it includes some of this, but not everything. Somewhere at the end there would be a CRC 32 of the block, and this is the end of the block. So at the end there is a CRC of all the things which are before, or maybe of the data only. We will check it out in a second. The CRC file, the CRC field here is pretty interesting because it's actually might be guessable for us. We might actually guess it. Yeah, and after one chunk, one block ends, then another one begins, and the last chunk in the file is actually called end. And it has a size of 0 basically, and a checksum which is constant, and that's the end of the file. So we do know what's at the last 12 bytes of the file already. We could use it for my solution. We are not going to use it. I know that some folks actually did use this information to as well as the known plaintext. It's already 12 bytes which you could use. But again, for my solution, I'm not going to use it. I'm just going to focus on whatever is here in this header and the next headers. Yeah, what could be the next headers? That's also a fair question. But before we get there, what is in this header? What do we know? And there isn't too much because we only have like this. And this is actually the width. Which means, you know, was the size in the horizontal size in pixels of the bitmap, and that's if we put our cursor on it and select Motorola for like big endian, we get the information that this is 640. So we know that the width of the PNG is 640. We don't know the height. The height might be 480, but maybe it's not, right? Maybe this is just like a red herring. And I don't think the height was actually this. I wasn't going to, you know, trick anyone. It's just like that. I didn't go for this height in the end. Okay, so there's a question why am I using 32 bytes here instead of 64 bytes for the SHA-256. That's because SHA-256 is 256 bits, which means it's 32 bytes. Or in hexadecimal representation, it's 64 characters. But it's not there in the hexadecimal representation, it's there in the raw digest representation, and that means it's only 32 bytes. Yeah, so it shouldn't be 64 is good. It should be 32. We can easily check it, by the way. So Python import hashlib SHA-256 or whatever, and let's do a length of just. Yeah, it's 32. If we would have hexadecimal representation, sorry, that's hex to just, then yeah, it's 64, but in normal raw representation it's 32. So that's fine. Cool. So now what we need to do is we need to look at some other PNG files and try to figure out what will be the possible next data which is there, and we also need to look at the specification of a PNG file. Let's start with grabbing some PNG files. Is this a PNG file? Is it? Yes, it is a PNG file, so I'm downloading it. Save image as and download. Let's grab some other PNG file. Can we find a PNG file here? Is this a PNG file? Copy image address. I don't know if it's a PNG file actually. I'm going to download it. Maybe it is a PNG file. Chrome actually says it is a PNG file. And Chrome is correct. It is a PNG file. So that, and we actually should get even more PNG files from like, so we have like a decent idea what could be there. I don't know. Let's just go to my site. Maybe I probably have some PNG files. This is a GIF, I think. This might be a JPEG. My photo is a JPEG. Oh, I know, right? What we can do, we can go to, not the dashboard, we can go here. And now we can press F12, we can go to network, we can select image, and we can filter by .png. And yeah, we have some PNGs. Quite a lot of them actually. Can I download them in some awesome way? No, it doesn't seem I can download them in an awesome way. So yeah. Alright, this one looks funny. Let me do this. No, it's fine. Okay. So I can just click save, and it saves. I'm going to grab a couple of ones from my site, because why not? There's an idea. Oh, perfect. We can look at the PNG specification from Anja. That's an excellent question, actually. So let's go here. A question has an excellent idea. And these are also in PNG, so I'm going to download one from Anj as well. No, it doesn't look like downloading. Is it downloading? Yeah, that's fine. Okay. Sorry. Misclick. Okay. Wait, because I actually wanted to grab, since we are already here, I wanted to also grab the PNG poster. Oh, these are like the normal posters, and I want the file formats. binary PNG. Please tell me where is a PNG. Yes, we can use PNG. Perfect. That's pretty small. Why is it so small? Oh, this is better. Okay. Yeah, so we'll be able to use it. So looking at the header, the I header, right? What we see is that there is the height, then there is the height, the width, then the height, then there is the bits per pixel, and bits per pixel are probably going to be 24. This is the default value, I would say, or 8. I do not expect anything else. Color, then we have RGB. If it's one of these, then it's probably going to be to compression, deflate. Yeah, PNG only has deflate. Filter only 0 is a valid number in PNG. You can look it up in the specification, by the way. Interlace is going to be either 0 or 1, well, but there is little reason to use interlace, and I don't think any encoder by default does that, so it's going to probably be 0, and then maybe we can actually calculate the CRC32 of the data, but we do not know the height, so yeah, so we do not know the CRC. This will be an unknown for us. We got what? Oh, and the height, I guess we can kinda estimate that given that the size is like this, then the height is probably going to be no more than this. And my guess is that the top bits, like the top 2 bytes, are going to be 0. That's my guess. I'm pretty sure that the height is not going to be more than 64,000. So yeah, we should get 2 bytes from here, then probably 1 byte here, 1 byte here. Yeah, that gives us already around 6 bytes. Then this actually suggests that there's an iData section afterwards, but that's not really true. There could be a number of sections after that, so we do need to take that into account. Okay, let's see at the PNGs basically, which I downloaded. So I'm going to drag it here, and let's go through them in hexadecimal one by one. Here we have that there is some fizz section, some time section, and then there's the IDAT section with data. So yeah, fizz section. Then if we go here, we have again the fizz section. It seems to be really popular, so maybe it's that. Then we have this, which again, this has a PLT section. PLTE is actually palette, and this is only for 8 byte bits per pixel. I do not expect this one to be 8 byte though, so let's ignore it for now. This one has sRGB, BKGD, then fizz. So we might suspect that there might be this section. This is a really small section, and it actually might give us quite a lot of information, so I hope it's there. I don't know what's there, but I hope it's there. If we look at another one, then we have a gamma section, which is even before the sRGB, and then again the fizz. And between these 3 sections and the end of the I header, we should be able to gather around 20 bytes of guessable data. Okay, is there anything else? Not really. Here, not really. Same thing, again the time thing. Something suspicious has sRGB, yeah, then a comment. Then this one has gamma and palette, oops. And this one has just IDAT. It doesn't have anything else. So we kinda already know that we should, there might be some other sections there, and we can, well, semi-brute force it, I guess. Okay, before we get to brute forcing, I actually want to implement this in Z3. Like the math we have there, I want to have it in Z3 because we will need that quite a lot actually. So how do we do that? I guess we are going to need to implement this thing in Z3, so let's do that. We actually don't import Z3, we import from Z3, we import everything. Okay, so yeah, let's re-implement it in Z3. So Z3 LSFR, LFSR, okay. Should it be like this, or should it be just... Yeah, it probably should be just a function. So in Z3, actually, when coding such a thing, what you need to remember is that you are not calculating the equation or the math which you give it. You are, or the expression. You are not calculating the expression, you are creating an equation. So yeah, and basically our equation is basically the polynomial, right? We don't know the polynomial, we need to know the polynomial, we know the output part of it, and we do know the initialization vector, which yeah, might give us something. Well, will give us something, but that's pretty obvious. In the end, yeah, what we need to find is one exert with CO, the constant, for the polynomial, ampersand, whatever the bit is. And this basically goes on and on and on for C1, B1, and so on. And this is basically, and so on, right? So this is our equation, and this is our unknown, this is our known. We do know these values. Some of them, not all of them, we do know some of them. And this is what we are looking for. We do need to find the polynomial. These values are important for us. Are there any other SAT solvers which are faster than Z3? Yeah, totally, and quite a lot of them. There's actually a competition almost every year where you can look for SAT competition, and you'll find like faster SAT solvers. By the way, Z3 isn't it's a SMT solver, right? And not only. So it's a abstraction step higher than a SAT solver. Cool. So this means that we are going to get the polynomial, I guess. So the poly. This is the CSS, just call it C. And then we are going to get the bits. And in case of Z3, this is actually, and I'm going to move it later, something called a bitvec val. It's a type which is a bit vector. A bit vector is like a register, right? With unknown values, again, unknown values. And you create it like this, you specify a name, so the, well, poly or C, doesn't matter. And then the size of it in bits, and we know it's 20, right? So this is what we're going to get here, and B is going to be probably more or less the same thing, but we will figure it out. Now what we return is basically the same thing which is here, but we need to write it in Z3 style. So what is the register state, by the way? Here, I guess the B is actually R, right? Is the register state. So let's call it like this, the register state. Okay. So first we need to grab the bit, and how to write this down, and this is going to be annoying. We need to extract the most significant bit, so bit number 19 from R. I think this is how it goes. I'm going to actually use the console from Z3 import all. Okay, so I'm going to create myself a bit val, which is, I don't know, ff and size of 8, bitvec val. Yeah. So z is a known vector value, and I want to extract from z, bit number 19 from z. No, exactly 3 arguments and 2 are given. Because I give it like a range of bits, not just one bit, a range of bits. So no, then maybe it's like this. What? Oh, wait, because I have to create this one 20 bits. Yeah, no, that's fine. Okay, and now it actually, again, this is an equation. It doesn't evaluate the equation, it just gives me the equation, and this is fine. This is what will extract the highest bit. So I extract the highest bit from the register, and this is what I will return. It is only part of what I will return, but I will return it as well. Okay, so, and this is, by the way, the size of it is only 1 bit. I think I can type sort, and sort it's not like sorting, it's like what sort of a thing it is. And it's this 1 bit, is the type of it. So this is what will be there, but I also need to create a bitvec of the size 1 and value 1. And masked is actually not going to be used this way. Instead, I'm going to do in xrange self size. Well, I know the size is 20, right? I'm actually going, you know what, I'm going to use this. I'm going to use this because I might have to experiment with it a little to get it actually running. So, and I don't want to change 20 to, for example, 8 in all places. That's why I prefer to use this. Okay, so new bit is going to be new bit exort with C. I'm going to extract bit number I from C. That's good, right? Yeah. Which has to be ANDed or multiplied. Again, multiplication and bitwise AND for 1 bit is the same thing, is the same operation. Just check it out if you don't believe me, like the math is the same. And I'm going to extract the same bit from the register state, right? R. And keep in mind that these are not values, these are expressions. So I will show you the expression in the end. Is going to be super scary, but we don't care. We don't have to solve it. Z3 will have to solve it for us. So it can be really complicated. The size of the expression can be really huge, and Z3 should still be able to solve it. Okay, so we XOR it by this, and C is our unknown, R is our semi-known or known value, which is fine. And now, after we do it, the new register, so new R, is going to be the old R, but shifted, right? And I'm going to actually cheat a little, and I'm going to just extract the upper bits, the bits from poly size minus 2, which is bit number 18, because 19 we had just shifted out, so 18 to 0 from R, and I'm going to add at the end of it, because I didn't shift it, but I can concatenate another bit to it. And I'm going to concatenate, so concat, is it how you write concat? Yeah, it's concat, okay. And I'm going to concatenate this with the new bit. So it's just like a bit concatenation, as in I'm going to get 19 bits from here, from this extraction, 1 bit here, and the 1 bit is going to be concatenated at the end of this, so I will get a 20-bit bit vector or register at the end. And now I need to return all the new things, and the new things are actually going to be, I guess I need to return the bit, I need to return the, I don't care about the new bit, but I do need to return the new register. Why do I need to return the new register? Because again, I'm returning an equation, a mathematical expression, and not a value. So I cannot change it in place, I have to wrap the equations around each other. Okay, so this actually looks fine. Cool. So I guess I'm going to copy it somewhere downstairs. Okay. Now, what I need to do is I need to I'm thinking what okay, I need to probably create a function around it, because I do need a function around it. So let's do it like this. Solve. Yeah, that's a great function name. I'm going to create, I do know I don't know the C. This is unknown. This is what we are looking for, right? I do know the initial registry state, so I do not have to do this. Instead of it, what I do have to do is, well, I do have to create a bit vec val, and by the way, this is only for, I need to do it 8 times, right? Because I have 8 register, sorry. So for I in this range 8, because I have, again, 8 random number generators. I need to create, so let's make C an array, and let's make register state an array as well. So C append this, and here I'm actually going to do an iterator. Yeah, okay. So these are our unknowns now, like in the plural form, like multiple of them. And yeah, we do basically the same for the bitvec val. We call it R. We don't really, no, we don't need to call it. It's so yeah, it's bitvec, just like that, right? Bitvec, yeah, that's fine. The size will be 20. Again, I do not want this. This should be poly size. It doesn't have to, the register state doesn't have to be named. I don't care about naming it, but I do have to give it a value. And the value is going to be, yeah, I do need to get this. KIV, I don't care about key IV right now, I care about cipher. So I do need to pass it the cipher IV to the self function. And now each of them is going to get this. So I'll just copy it. Yeah, it will grab the 20 bits and put it here. Okay. So now I have both the arrays ready. And now what I need to do is I basically need to call, well, I can ignore the 21st bits, right? I do not need to do anything interesting with them. But I do need to store the equation. So let's do like this. Let me think if I'm not doing something really bad. No, it should be fine. So for I in like j in x range 20, I can ignore the first 20 calls to this, but I do need to keep the references. So what I am going to do is r is equal to, oh, actually new bit, like bit, and r is equal to zfr, blah blah blah. No wait, for I in x range 8, I need to do that for all of them. And call it with C of I, and this is also of, just call it new R. Okay. C of I, this is my polynomial, and the registry state is R of I. And then the R of I is going to be equal to the new R of I, and I do it 20 times because I don't care. And this is the moment where I start caring about the result. So what I need to do now basically is I need to do the same thing for however many bytes I actually do know. And I know that the next 2 bytes are zeros, right? So let's do somewhere here, I'm going to do an array of the bytes which I know, starting from the 20th byte. And if I don't know a byte, I'm going to put known in there, I guess. So known bytes. And like, starting from byte 20. Okay. So I'm wondering, because in addition to that, I do need to give it, I guess I can maybe copy these bytes just like this. So I can put it there anyway. C source extract. So these are the bytes from the file, which I know are correct, so I'm not starting with 20. Then I do need the data, because the data will, I will have to XOR the known bytes with the data. And now is where the guessing starts, right? So what's after that? And after that is the height. And the height, as I said, it will probably have two zeros. So 0, 0. So this is the height. And then I have no idea what the other two bytes are. So I'm just going to put none there. And then, sorry, where is this? Yeah. Then there will be the BPP, which is bits per pixel. And bits per pixel, I said is probably going to be 24, which is, I guess let's look at this file. Yeah, here we go. Actually, yeah, it should be visible here. Header and, okay, why is it? Sorry, where's the, okay, I need to actually look at it a little closer. The size is really, did I have to select the file which has a weird size which I cannot calculate in my head? Okay, so hex 1115. No. Like this. Okay, 221. So that's DD. Okay. So this file I know. Oh, it's actually 8-bit. So let me select a different file. Do I have a file which is, oh, this one that was funny. It was actually 24 bits. So let's look at this one. What I'm actually trying to determine is it. This is the size, and then. Okay, so what I'm trying to determine is it bits per pixel or is it bits per color? Because PNG is actually capable of having more than 8 bits per color, which would mean even more. So yeah, it looks like 8 is the proper value for me to put there. It is, yeah, 24 bits. Okay, give me the PNG specification because I'm starting to get lost and I don't like it. Next page. Header, okay, color. Bit depth is a single byte integer given bits of per sample. So it's per sample. So yeah, 8. We will have 8 there. Not 24 as I was saying all the time, but 8. So bit depth. 8. Okay, we know this one. Then we have the color type, and the color type is either grayscale, RGB. I'm assuming it's going to be RGB. I don't think, yeah, we might have to brute force this, but as long as we don't have to, I'm going to say that yeah, the color type is going to be 2. And then we have the compression method. The compression method, there's only one compression method. It has to be 0. There is no other compression method in Python. So compression method is going to be 0. You know what? This is starting to be a little more verbose. Let's do it like this. Color type. Okay, and then compression. Okay, so that's fine. Now after the compression we do have, what did we have there? Filter, and filter also is 0, because there is no other filtering method. There's only one filter method, that's the adaptive filtering. Filters in PNG are pretty cool, by the way. And we have interlace. I'm pretty sure there is no interlacing. But yeah, but this might be like, this might be 1 and this might be different. Okay, so let's assume these are only the bytes which I know, and for now what I'm going to do here is I'm going to basically do it like this. For j in x range of 20 and length of the known bytes. I want to, well, first get the known byte, which is the known bytes of I. Whoa, okay, that's fine. Which is XORed by the data. And I'm actually going to assume that the data here is a byte array. Yeah. Data of J. And this is the known byte, so the data is again the known byte XORed with the output and sorry, so this is the output byte, like the key stream byte. So, or the output of all the 8 registers. So the output or the key stream byte from the equation is going to be basically this. So I need to get, yeah, I need to run all of them, and I need to store the bit this time. So bits is going to be this, and bits that append bit. Now I have the bits, and now the key itself is going to be concat, and I'm just going to concatenate all the bits. So bit 0. Wait. Bit 7. Okay. So bit 7, bit 6, bit 5, bit 4, bit 3, bit 2, and bit 1. And 0, obviously. So this is my bit. And now I need to tell it that these two things, actually the known byte and this, the output of the equation, they actually need to match. Because if they don't match, that means that I have the wrong polynomial. And yeah, this is basically the equation part of the equation. Something which I know has to match something which I don't know. And the unknowns being the polynomial again. So to do that, I need to create a solver. So S is a solver. And I need to give it constraints, or actually the equations. It's actually more like constraints, but whatever. So I need to add the constraint that keystream byte equal, so the equation, this has to be equal to that thing. Now this I might want to do bit vec val here, or like bit vector here, but it will be automatically converted anyway. And I need them to match. They need to be identical, and all the constraints I add need to be met. So after this is added, and by the way, there's one more thing here. I need to do this, I need to do this here. I am going to do this. I need to do this, by the way, for almost everything, because I need to roll the pseudo-random number generator anyway. But this part is actually done only for the bits I know. If I don't know the bits then of the plaintext, then I cannot do it. So if known bytes of I is not known, then I can do this. Okay. And here we get, at the end of everything, we get an equation. I'm pretty sure you want to see the equation, right? So let's print out the equation. Start then, wait. I do not need this, and I do need to call the solver. So, yeah, whatever. Solver, is it how it's called? No, it's called solve, right? Solve with a lowercase s. Solve. And I need to give it the cipher ID, and I need to give it the data. Okay, and it says parse error, which means I did something wrong, but we will fix it in a second. Wait, what did I do wrong? At what point is it complaining, by the way? Blah blah blah, append with vecval here. It's complaining here that... Why are you complaining? Is it... Did I mix up the order? Yeah, I think I know what I did. These are like actually the other way, like this. Yeah. Should be fine now. Okay, gets better. Poly as Z is not defined. Where am I using it? Here. Okay. Okay, that's fine. What? Here the bits are being, oh, it's bits, not bit, my bad. Okay. Okay, perfect. We do have the equation, and the equation is too large, it's so large actually that it puts like dots here. So yeah, we cannot actually see the equation because it tries to shield us from the amount of math which will be going on here. Thankfully, it's really easy math, so like math without any additions and without any multiplications is easy math for Z3. So now what we will tell it is like actually do check if it's solvable. So as check and run check. I think it's check, or was it check? Now let's see. Yeah, sat means that the equation has been satisfied, which means it did find some values which meet this. Now, please note that we have here 1, 2, 3, 4, 5, 6, 7, 8, 7 bytes actually, and 7 bytes out of 20, which we need, means there is a lot of different results. It by default gives us only one, and the one is not going to work because the probability of it working is like really bad. We might brute force it, but yeah, I guess we can try brute forcing it. So to brute force it is like this. First of all, we check if CA, this is quite funny, I never remember it, like _m or something like that. R, yeah. ch.r is equal to, no, let's print it. I think it's like -1 is actually okay, or 1 is okay. Okay, if it's equal to 1, that means it has been satisfied. If it's equals to 0, it means it is no longer able to satisfy it, so it cannot find any other solutions. And that's fine. Let's just get out of here. What I wanted is I want to get all the solutions. Now, if I know it's satisfiable, then I want to know what are the values that are unknown to me, like what is the polynomial that you found that satisfies this output, right? And to do that is, we actually need to get the model, and that's what we do using model. And from the model, we can get the values, and that's actually kind of funny how you do it. For example, if you print the model, and let's do like that, you basically get the values. These are the values for all the, because I have this, never mind. Yeah, these are basically the polynomials for our values, but to get the value itself, we need to do C0. This is one value. By the way, let me do break here. By default, it doesn't. It doesn't return the next solution, and so that's fine. And I need to do, I think, as long. Yes, okay, I do remember my Z3 a little at least. And this is the this is basically the polynomial we got. So this would be the poly. Now, let's do it like this. So the polynomials for I in X range of 8, poly, append, and we add the polynomial to it. So yeah. Okay, and now having all these polynomials, what we can do is we can, actually, well, we can do it a little differently. We should actually do it a little should just concatenate it. Doesn't matter. Having the polynomial, we can try to decrypt the data. And we do have a function to decrypt the data. And after we decrypt the data, do remember that there is the hash of the data at the end, right? The encrypted hash. So we also decrypt the hash and we check if it match. If it match, yes, we won. If it doesn't match, well, too bad, right? So, okay. Yeah, how do we decrypt the data having the polynomials in such a funny form? We need to probably change this a little. Because, yeah, we don't have this, we don't have this, we have this. So I'm actually going to copy paste this. And I'm going to create a new one, which is called mine, or solve. And I'm not playing with bit streams anymore because I don't care about them too much. I also don't care about the key. I don't care about this either. What I do care about is I care about this. So I'm going to go with it like this. I'm going to give it the cipher IVs and the key IVs. The keys are actually going to be the arrays. And I'm not doing this, like polysizes. No. So keys and cipher IVs, and these will be just numbers. So here I actually give it the keys of I, and here I just give it the cipher IV of I. Or actually, it will be a little easier for me if I just go with a normal cipher IV. So yeah, let's do it like this. Because, you know, the form of the data which I get is incompatible with, because I have numbers. I don't get bit streams, I could convert them to hex and so on, but I just don't want to do it. Okay, and then this should be fine. So let's see if this works. So solve, yeah, it doesn't solve anything. It's just the same function basically. Okay, so here. And we create this, we give it the polynomials, as I mentioned. We give it, what else do we give it? No. Here, we give it the polynomials and we give it the cipher IV. So we have the cipher IV, so we can give it. Okay. And yeah, we get like a C. And then we can call the C crypt on data, but we are not getting the data. Or are we getting? Yeah, we are getting the data. We are not getting the encrypted hash, and we do need to get the encrypted hash as well. Oh, encrypted hash. And we crypt the data. Then we crypt the hash, encrypted hash. And then what we do is we do a hashlib.sha256 of the decrypted data. So this is like decrypted data and decrypted hash. We calculate the hash of the decrypted data, and that's like dec data hash. And we get the digest, of course, which is the hash, right? And now we check if the decrypted data decrypted hash is equal to decrypted data hash. So yeah, if we decrypted data is the same as this, because if it is, that's it, solved. So what we can do is like print, yeah, and write it to a file. Open with open flag.png, write binary as f write the decrypted data. Okay, and that's it, like return. We don't have to do anything, we just need one solution. By the way, there is more than one solution, like more than one key will decrypt the data. This is because some polynomials for some initialization vector in this LS linear feed shift back registers actually generate the same key stream. That's how it works. If you get into the math which is behind it, that's kind of obvious. So there are more than one solution which will work. Okay, otherwise what we do, we actually add to our solver another constraint, and that constraint is for the but let's run it. But the constraint which we will add is basically the solution has to be different. Okay, and it says something, 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 something. What do you mean? See cipher data. And key stream byte. And does the data have to be... Sorry, cipher does create... Oh, why is it complaining? So crypt solved. Cipher data and cache, right? And we call it with data. So crypt data, this print type plus. It's a byte array, that's fine, right? Because we get a byte array out of it anyway. Oh, this probably returns something here. Get bit, okay. And the get bit we get, there is, what? Line 177, I have something incorrect here. If known bytes, then this looks fine to me. Because here is one loop, but actually gets the bits, and here's the other loop, which is actually using the bits. It looks fine, actually, to me. Okay. Wait, what does it say that it cannot use this? So R is a string. Why is R a string here? Type of maybe. String, string, string. Why is it a string? We created here. We get a bit stream out of this. And then, oh, right, sorry, my bad. Yeah, that's fully my bad. Here we go. Yeah, okay, that's fine. It obviously didn't write, yeah, because we have a really low probability of it actually working. So, what we need to do now is, again, add the constraint. So, as add, and the constraint is for the result to be different. So it would be great for me to add all the to add basically all the polynomials together to form one big thing. Where they have the polynomials? I have them here, and they are they are here. Okay, so perfect. So current poly is equal to concat of this of 0. Sorry, well, it doesn't matter. 7. Okay. So I'm going just to concatenate the polynomials to form a really long register. This is fine. Okay. And 0. Okay. And I'm going to concatenate, do like exactly the same, but not on the current polynomials, but on all of the polynomials. So this is going to happen here. So like all poly, let's call it all C. And I'm just going to remove this. Yeah. Yeah, and now I'm going to tell it, so yeah, listen, the solution you get to me, it actually has to be different than the one you got now. And I continue. Okay, let's see. It would actually be great if I would display like something like this. Counter is equal to 1 or like 0. If counter is equal to 0, print dot. Okay, so I actually know it's working, and I'm actually going to decrease it because it's not going to be that fast. No. Now, I can leave it like that, or I can actually look for some more probable known bytes. If I find a known byte, then that's actually great, because that will really increase the speed of it, as in if I find 20 bytes, it will be instantaneous. So, let's find the next bytes then. I have it done to... Oh, by the way, there's one thing I want to check. Let's assume that the interlace is actually 1, so I'm going to put 1 here. That still works. Okay. If we find a proper, like, if we find some number of bytes, it will be able to tell us, hey, actually the byte which you added, which you claim that is a good byte, is actually not a good byte. Because it will know that there will be no chance for any of the polynomials which are possible to generate this kind of output. Cool. So what we know now is that there is the... well, there is the checksum. We have no idea what the checksum is. And now probably what we will get is we will get, I guess, sRGB-ish. That was the popular thing, right? We will either get the sRGB thing or maybe the gamma thing. There was also this. And the order would actually be like this, like gamma, sRGB, and fizz. Let's assume that we are going to get like the gamma first. It's just an assumption, I don't know. Let's see in the specification what's actually like P and G gamma, what is it? Okay, so the PNG specification says that gamma. Okay, gamma is chunk contains 4 bytes, and that's the gamma. And if it's 4 bytes, I hope it's not gamma. Okay. Yeah, I'm still wondering how probable it is that it will be there. Let's go with sRGB, because I saw it in actually more of the chunks. The gamma is like, it doesn't ring a bell. So let's try with sRGB. And this is what? Oh, did I interrupt it? No, please continue by all means. Okay, so sRGB contains 1 byte, and it's either 0, 1, 2, or 3. And in this case, for example, we have sRGB, it's a 0, so let's put 0. So okay, let's assume that this is sRGB actually. So we know the size, right? The size is going to be, no, it happened. Yeah. The size of it is going to be 1. So we know that the bytes are going to be like this. So we know 4 more bytes. Perfect. Then we know that it's going to be sRGB, right? So that's 0x73, then 0x52, then 0x47, and 0x42. Yeah, I'm getting this from here. And then the value is unknown, but it's probably going to be either 0 to 4 to 3, right? I could mark it as unknown. I'm going to go with 0. And then the checksum. And since I'm going with 0, I'm just going to grab the checksum as well. So the checksum is going to be A, E, C, E, 1C, and then E9. Okay. So yeah, this gave us actually 12, 13 new bytes, so it should be almost enough. So let's restart it. And it says model not available, which means, yeah, something broke. So it's like this. I'm going to print CHR here. -1, -1, yeah, so that means return. That means we have something not right. And you know what? Instead of a dot, I'm going to print actually the counter. And the counter, oh, I'm never incrementing the counter, so it means it's really, really slow. Okay. Okay, yeah. So if it's really, really slow, then let's just go with this. I got a hash of a hash. Where did I get a hash? Oh, here. Thank you. Aboba, thank you. That is true. Okay, unsat means it's not satisfiable using this way. So let me remove it and let me try to brute force it once again like this. Okay. Yeah, it's really slow. You know what we do with slow things? We run it in PyPy. PyPy doesn't have Z3 installed, really funny. Okay, so if we know it's unsatisfiable, let's try it like this. Can we satisfy it with this? With a length of 1. Or actually what we could do here, I guess, is like we can remove this. Let's assume that we actually get this correct, and we get none here, because we don't know it. And this means also we don't know this part. So I'm assuming that we got the chunk right, but we have no idea what is in the chunk. And let's see if this is satisfiable. Unsatisfiable. So this is probably not the correct chunk. The chunk is probably not there, or I made a typo. Let's see if I made a typo. So it's 73, 52, 47, 42. So we know that this is not this one. Maybe gamma. Let's try with gamma. So gamma is the size of 4. So I'm going to comment this out. This might come in handy later after all. So 4, and then we get the gamma, which is OX 67, OX 41, OX 4D, and OX 41 again. Perfect. Then I have no idea what, and this is the data which is in the gamma, and then I have no idea of the checksum. I actually shouldn't put this here because this makes the equation a little more funky. Unsat. This is not funny. Okay, so if it's not gamma, perhaps it is fizz. So let's try with the fizz section. The fizz section is size of 9. Okay. So the fizz section is the size of 9, and then we get OX 70, OX 48, OX 59, and OX 73. Let's try with this section. Unsat. Okay, this is getting ridiculous. So we tried gamma, we tried this, we tried this. I'm doing something wrong because it should be one of these sections. We can, I guess, comment this out and try it to brute force a little more, and I'm going to look at other PNGs. Now, you know what? I'm actually going to cheat a little because we are already 10 minutes over time, so I'm going to cheat a little and I'm going to look at the real flag, like what is at the beginning of the real flag. I just note that when making the challenge, I actually did test it blind without knowing what is the format of a real one, so it is solvable. Oh, thank you for the donation. Yeah, I don't think it actually like Unicode works, but nice attempt at the injection. Do I have Z3 under Windows? Because if I have Z3 under Windows, it will be way faster. So let me just check if I have it. Oh, I don't have it. So like, if I would have PyPy, that would be actually way faster. What? Oh, no, wait, J. Yeah, thank you, Foxtrot. Yeah, this was a huge mistake. Let's try it again. And I am going to try to uncomment some of the stuff which was previously commented out. So I will start with this one. Oh, Dasm and Viechu, thank you for actually that, for pointing that out. Okay, now we're getting somewhere, it's getting satisfiable. Okay, now what if I actually do try the 0 here again and I try this again? Come on, come on. Okay, save it and run it again. Let me look at the code again, if I didn't make any other obvious typos. So this is J, known bytes is not known, then, okay, data J with known bytes of I. No, this is again correct here. Okay, then I exit it. Okay, this should be fine now. Let's try it now. And it's thinking. Yeah, it got really slow now. Why did it get very slow though? Shouldn't get any slower. Okay, it still is satisfiable, which is good. So let's try now if we can get one of these sections to be after there, because if so, wait, we might actually have enough bytes to get it solved. Yeah, let's do it like this. So let's press Ctrl C. If this doesn't work, I'm going to go for my default solver and try to run it. Or maybe I will leave it as an exercise to, to solve it. Am I getting the order here correct? Yeah, the order should be correct here. Poly, that should be fine. Data hash, yeah, this should be fine. Why did it get so slow though? Seriously, do I need to kill it? Kill the okay. Did I forget a comma? Seems so. Yeah. Okay. If this doesn't find the solution, then well, I guess I'm going to find my solver and just run it. My solver is basically built around the same way. So, yeah. Okay, and I'm also going to... Okay, so this is the original flag file. And we have an sRGB, then gamma, and then fizz. So we have, I think we have the we guessed the correct stuff. So yeah, this has a 0, so we have all the bytes known, we do know it. Then we have the gamma, and the gamma has 4, and yeah, so this is what we have, and this is 12 plus another 8, this is 20 bytes. We have, yeah, and we got the solution. Perfect, so let's look at the flag. Here we go. The flag is CTF something something 1337, and this is by way of a PNG. The size, as you can probably see, or maybe you cannot see it. Yeah, the size is 360, so it wasn't 480. It was like a panorama size. So okay, in the end it did work actually. Thank you for noticing the typos, and yeah, we didn't have to look at my solver, the original one, which I used for testing. Anyway, I guess that's it. I'm quite happy that it did work in the end. And yeah, but this is what the task was about. I'm going to take a look if there are any other questions. Again, I'm going to upload the solver to my GitHub if you want to take a look. And I guess the tip here is that Z3 is really cool. By the way, you could have solved this task using brute forcing and known plaintext as well. There was another way to solve it. This is not the only way to solve it. Perfect. Okay, let's close it. Yeah, I'm quite happy that it actually worked. Oh, Pavel, thank you for the donation. Yeah, totally. That's my feeling right now. Let's look at the questions. The questions will appear downstairs. Oh, about the rootkit in UEFI, I have a link from Przemek. I'm going to give you a link on the channels, I guess, if you want to follow it up and tweet about it. Okay. Okay. Yeah. Yeah. this title, Crumbs, unremovable crapware. I didn't even know that there is such a thing as crapware, but it seems there is. Thank you for the link. I'm going to go through it later on. Sounds interesting. On yesterday's Patch Tuesday, the amount of fixed bugs was very small. Why is that? Haven't people found more bugs? That's a good question. Maybe it's, you know, vacation season or something. I don't know. No idea. Maybe all the usual Windows bug hunters actually went to look at Intel and speculative execution. No idea. I can only speculate on it. To work in Switzerland, you need only English or German and also French. It depends on the company. I mean, at my company we speak in English. There are other companies, obviously, where you are required to speak either German or French or Italian, depending on the part of Switzerland you're in. So it depends on the company. How difficult would be automate every Google CTF step Quals with a script? It's a good question. Pretty bothersome in some cases, but you can, I guess most of the stuff you could automate with a script one way or the other. But it would have to be a custom script for a given task. You couldn't write a script which you press enter and it solves a CTF like this, right? That's just not doable. But for a given CTF, you could probably write a set of exploits. There are some exceptions for that. Like if it comes to like image recognition, then probably it gets shady, right? If there was a task like that. Or there might be like issues like it's rather hard to emulate something. I don't think it's worth like automating everything in a CTF, like while solving a CTF. You automate half of the stuff, the other half of the stuff you do manually. And I do not mean literally half, like part of the stuff. A more general question, and I know the answer is depends on you. I've got accepted to a prestigious university for an InfoSec Masters. I also have an interview for a pentester. Which one do you believe would be beneficial? Depends on you. So it's like this. Depends on which moment of a career are you in? If you already have like 5 years of experience in the industry, of a professional experience, so you know the master's equivalent, then you might think about actually going for a pen tester. Otherwise, you might want to go for the uni, because you might actually learn some more stuff, and at the end also start from a higher salary level, I guess, because usually that would happen. So yeah, it depends. Yeah, both options are rather good, I would say. Have you ever seen a program reverse engineered back to source code? Somewhat, sort of, right? Because you cannot, well, the old joke goes, you cannot recover comments, right? You cannot recover comments which were in the source code. That's just not possible because they are not in the assembly. Apart from that, give or take, there are some cases like that, not a lot. Like, I don't know if Open Transport Tycoon Deluxe wasn't like that at the beginning. Is there a summer game dev challenge soon? Yes, really soon. Seriously, probably this week or at the beginning of the next. But yeah, there will be again the summer game dev challenge. Is there a place where you can post your own CrzaQ and let people solve them, like CrzaQ.de? Yeah, CrzaQ.de is not there anymore. Marbel, thank you for the donation. White space, tab, white space. Yeah, I agree. Currently, I'm not sure, but do look at wechild.net or wechild.org, and if there are any sites where you can donate your own challenges. Apart from that, nothing comes to my mind, in all honesty. It's a good question, a really good question, though. I watched CrzaQ's podcast where he said the Nintendo Switch hack jailbreak destroys a console once you try to reverse the bug code. How this protection works? I have no idea. I would have to look into it. Try asking some folks from the Nintendo Switch hacking scene. They probably do know. But yeah, I have no idea. That's kind of weird. You could work on stream sound levels. Music is significantly louder than your voice. Voice level is generally lower compared to video media. Maybe decrease music level. Okay, fair enough. I need to do some experiments, but that's fair. Thanks for the feedback. Is this technically possible to encrypt an archive really securely based on password? Yeah, sure. Like, just use any modern encryption like AES. And the password has to be good, of course, because if you can brute force the password and therefore brute force the key, then yeah, sorry. Isn't that XORing with zeros, which was the key, the way how CrzaQ attack on Linux implementation of WPA2 worked? I, in honesty, don't remember. Yeah, I don't remember. I did read that paper, but I don't remember. Sorry. Why Google employee isn't using WebP for their blog images? Because it's a personal blog. smtcomp.sourceforge.net. That's the SMT. Okay, that sounds like a cool link. So thank you, Foxtrot. I'm going to pass it around. I don't know what's there, but yeah. Have you read Windows internals? Not all of it, part of it, not the newest one. I need to catch up on it. I read it when it was like 4th edition, 5th edition. Have you heard about Cicada? Yeah, I did. I never tried solving it though. If you don't know, it's like a let's call it a hacking competition for the large community, and it's basically a competition which involves the competition is a challenge, a riddle, which basically involves also doing physical actions in the different parts of the world. So people usually like team up and try to solve it. But yeah, I just read about it, I never tried it. Any comment about the quiz? Let's see the quiz. Okay, so this was the quiz for today. From Guest. Thank you, Guest, for making it. If you don't know, Guest is basically pasting the links to the quiz, or Foxtrot is, or whatever moderator is there, on our chats before the stream. Well, okay. Okay, I guess there's like, what's your experience related to the following question? Zip contains, okay, so zip contains central directory header, yes. A local file header, so this one, yes. No, no. End of central directory, yeah. And no, so that would be this one, and this one. I guess I have to, I'm a beginner, yeah. No, this one. Let's see how good am I. What are reading methods? Start last or like end first? Okay. Oh, this is, by the way, just my terminology. It's not like the actual terminology for it. It's just something I made up. So this is start first, and stream. Yeah, and again, it's something I made up. It's not like official terminology. Okay. Data goes with local file header. Marble, thank you for the donation again. Is it more white spaces? Or are you testing if I read the white spaces correctly last time? Yeah, thank you for the donation. Zip CRC32 polynomial is this one. I don't know. I'm guessing. I think it's this one. I don't know, seriously. CRC must be in the clear. So it doesn't have to be in the clear, by the way. So I'm going to go with false. There is a way to do it that is not in the clear, but by default, it's in some implementation it is in the clear. 5.6 is the implementation of, a signature of. I'm pretty sure that's the local file header, and I'm pretty sure I will get this wrong. Legacy zip crypto. Still used, yeah, totally. Really good backward compatibility, well, yeah. Technically, byte-based stream cipher, it is. And non-plainted, yeah, it is, with further, yeah, I guess all of them. Legacy zip crypto, yeah, there are 3 registers, 32-bit is, that's true. Wow, wow, okay, wow, this is getting really hardcore, guest. Let me think. CRC key 0 and CHR, then we have okay, where's the, yeah, you're not making it easy. This one is, by the way, key 3, because this is the least significant byte, and key 3 is actually this. This uses key 0 and the char, so this should be this, and this is using key 2 and key 1, so this is it, which means it goes like this. So that's my, I hope that's the case. Legacy zip crypto attack simplified, minimum of 20 bytes of known plaintext. No, you can have less. Of compressed. No, you can have less. Oh, what do you mean by compressed plaintext? If you have the compressed stuff, then it's 13 bytes, I think it's enough. If you have real plaintext, then, and it's compressed, then it's 20 bytes. So I would go with a no here. Compressed is the keyword here. Yeah, that's true. Takes a few minutes to run, basically. In some cases, we can even get the password. That is true, but only if the password is really, really short. The quiz was like super difficult. And show results. Let's see. Oh, I almost got everything. Okay, this one I got correct. This one I got correct. Data goes with LFH. Yeah, this is correct. Oh, I guessed the polynomial call. I didn't guess this one. Yeah, I know. Okay, that's true. Yeah, I should have figured it out, actually. So this is my bad. Yeah, this is true. This is true. True. Okay. Yeah, cool. So thank you, guest, for making the quiz, and yeah, I'm looking forward to the next one. We should start publishing the results of a quiz somewhere. Yeah, let's chat about it, guys. So that's it for today. I guess there's also a link to the presentation. I guess if you go to my blog, there is the links to the zip presentation somewhere there, so you don't have to retype it. The best encryption system that has proven itself for thousands of years is RSA, but are there any faster but also simple and secure encryption systems? Well, elliptic curves are generally faster than RSA and haven't been broken yet. I'm not sure about the thousands of years for RSA though, but yeah, it's pretty decent so far. So elliptic curves seem to be the new hotness, and they are faster and they are smaller than RSA for the key size. So yeah, but that's about all I know about them. So that's it. Sorry that it took so long today. Thank you for being here. Thank you, Foxtrot, for being the moderator today. And yeah, and that's it. So see you tomorrow on the Polish stream if you speak Polish, and see you in 2 weeks. If you don't, because the next live stream is going to be in 2 weeks, so we skip the next week. So that's it. Thank you. Have a great evening, and see you next time. Bye bye. Happy hacking. I'm going to leave you with some music.